APS water resources section. Junfeng has been involved in a groundwater study in the Rogersville and Berea sandstone development area. He's going to tell us a little bit about the baseline data project that he's been working on. So please welcome Junfeng.
Thank you all. I give my name there. My name is Junfeng. We are still working on this project, so I'm just trying to give an update on what we have done so far. The reason we do this baseline groundwater assessment is the hydraulic fracturing horizontal wells can have some potential impacts on groundwater aquifers. Typically, each of those wells can produce a lot of wastewater in the order of millions of gallons. Those wastewater, if not handled properly, it can leak. This one from the surface that can lead to contamination of surface water and groundwater. Another potential pathway is the well bore. If it's not sealed properly, and when the wastewater flowing back on the surface, it can go into the aquifers as well. Another aspect is on the sections of the horizontal fracturing, not just the wastewater, and also the methane or oil immobilized by those high pressure water. If those gas somehow are close to a natural fault, that can also potentially going up, contaminate groundwater aquifers. Well, those are theoretical pathways so we can think of. Not necessarily saying that when doing hydraulic fracturing, groundwater on top is going to be contaminated. But this is the potential risk there. The reason we want to do this project is because we have currently Berea sandstones going on with hydraulic fracturing. One concern is, although it's in small scale in terms of wastewater, and the fracking depth is less than 2,000 feet. Actually, some of them even shallower than 1,000 feet. Typically, those fracking sites much deeper. For example, Masas Shale is about 1 mile deep. So another perspective is Rogersville. They mentioned is on the really early stage, but that's more like a typical unconventional reservoir. If India is developed, it's going to produce wastewater comparable to other typical big sites in other locations of the nation. We have groundwater data repository, but we do have a lot of water chemistry data, but those data have been collected from different sources, different purposes. Not many of data points that are actually relevant or related to that we can use to assess the potential contamination from those hydraulic fracturing activities. So what we need is to collect new data, water chemistry, that we think that it can help us understand contamination, possible contamination from hydraulic fracturing. So we need to collect new data. So that means we need funding. Through an organization called Environmental Friendly Drilling Program, KGS is a part of a partner. We get into contact with a company called GSI in Texas. They have a project with Leipzig, which is part of DOE. GSI is looking into develop advanced analytical methods to looking at environmental issues associated with hydraulic fracturing, one of which is the baseline sampling and straight gas investigation. What they've been doing is they're trying to develop a protocol to improve data collection, data analysis. So they develop those protocols, and they are looking for field sites that help them to evaluate the protocols. So this is one part of the study, develop sampling protocol for water wells, sample analysis, collection. We need a field site. So for us, we're interested to get a baseline water capture data, so the all we got together work on this project. So it's sort of a good cooperation between my company and us. So we started this project actually in March. We started in field sampling. First, I'd like to thank the field team, board. Let me check this. Bart, Steve, Richard. Those three guys went out 8 weeks in a row, every week, to East Kentucky, collected 51 samples. And those are the photos when they're doing their field work. And photo here shows two people from the company, and Glenn Beck and me are the backup team. They never need a backup. They did all the sampling by this team 8 weeks in a row. Also, I'd like to thank UK Agriculture Extension Office. They are tremendously helpful for us to locate water wells in the eastern Kentucky counties. I'll briefly talk about the field sampling procedure. You go there, you collect well information. For each well, we have to fill up 10 pages of information based on the protocol. Then we're going to purge the water well. That's essential step so that we're not collecting the water sitting in the well for a long time. You want to get the water from the aquifer from the formation. Then we collected the samples. Then we ship the samples out to the labs. We have 3 labs to analysis. One for major chemistry, this is done by a KGS lab. Another is dissolved gases, mainly methane. This is done by a lab in Pennsylvania. Another type of analysis we did is isotope analysis with a company in Illinois. So we did 51 samples in 8 weeks. I'm still getting more data, but I'm just trying to share the data analysis with you guys. This is very preliminary analysis. First, our focus is on dissolved methane first, and the image there shows the locations of the wells in those counties, and different color and the size of the dots represent the concentrations of methanes in those wells. You can see all of the wells is pretty scattered throughout these counties. And among the 51 wells, we have actually 40 wells have detectable methane content. We have 26 wells have methane above 1 milligram per liter. That actually a little bit got me surprised. We didn't think that we're going to see so many wells going to have elevated methane content. And there are also 12 wells have methane content above 10 milligram per liter. I want to mention that in the KGS database, we don't have a column called methane, and actually in our EPA's drinking water standard, there's no item for methane as well, because methane itself is not toxic and it's not poisonous, but the U.S. Office of Surface Mining has a guideline for dissolved methane in groundwater. The action level is 10 milligram per liter. They suggest well owner to do some remediation because methane is flammable. If they are accumulating in a closed space to a certain concentration, it can be dangerous, cause explosion. It can also cause suffocation. We also, besides methane, we also did water chemistry analysis. We're trying to understand if any correlation between methane concentration and general water chemistry. This is a blank diagram, Piper diagram. That's a very common tool for water chemists to understand the general water chemistry. You normally plot your cations, those positive charged particles on the left triangle. Then you plot the major anions, which is negative charged particle on this side. Then you project your numbers to this diamond. Each water sample gonna be one point in those diamonds. Depending on where they're located, they can tell you roughly what type of water after this water gonna be. In a broad sense, if your point located in this region, meaning you have calcium bicarbonate water, which means always shallow, freshwater water. If you locate it in this region, commonly referred to sodium bicarbonate water, here water is deeper. And then if your water chemistry point located here, often your water is going to be deep ancient groundwater from the top. You have a high sulfate concentration. This can be from gypsum or may also possible from mine drainage. Now here I plot the water chemistry data from all the 51 water samples. You can see primarily we have two types of waters. One is calcium bicarbonate, another is sodium bicarbonate. I also look at it how those different waters relate compared to methane concentration. In this region, we have about 18 wells belong to calcium bicarbonate water. 4 of the wells have concentration about 1 milligram per liter. On this, on this region, sodium bicarbonate water, we also have 18 wells. In this region, we actually have 14 of them got higher methane concentration. So you can see that the methane concentration actually somehow related to general water chemistry. this type of water tends to have high methane concentration than the calcium bicarbonate water. Another region, this ancient water, we have two wells, and 2 wells got high methane concentration. So we just, and then on this region, those calcium sulfate water, we also have 2 wells, none of the methane concentration. So another question we need to ask is, forget about this, is another type. Those the wells that located in the middle, still have like almost half of them have high methane concentration. One question to answer is, with all the methane concentration, where are those methane coming from? In a broad sense, methane comes from biogenic or thermogenic. If you plot the isotope signatures in methane, you can broadly divide the methane from regions, like here, this is biogenic, thermogenic. This often referred to methane generated in deep, like shale gas. Here, it often happens near the surface, like shallow groundwater. I'm still waiting for the isotope results, but I do have some points here. Those red dots are from our samples. You can see most of them, they are biogenic gas, means they are shallow source. Those blue diamonds are our data provided by our energy section. This is a Mississippi Devonian gas, isotope signature. Those are, see those refer to, those are into the thermogenic category. You can see, so far, I think most of this methane gas in water wells actually is shallow source. With that, I think I'm done. Here are just acknowledgements. I would be happy to answer any question you have.